My name is Robert Friskney. I work for Arista, and we make lovely routers. But the best thing you can put in your router is a very exciting optic. High-speed routers do not do much without optics. So I hope you love talking about them, because that is what's stopping you getting to the beer. So Dave asked me to talk about the new things that's happening in this world. We are fundamentally changing how we're doing optics in routers with the technologies we're listing here. So the first thing I want to talk about is why. Things are changing in how we build routers, which give us these opportunities. First thing, when I was young, which is many thousands of years ago, chips were about the size of my little fingernail, and they went in one package. And we don't do that anymore. Instead, you have multi-chip modules, where you have multiple chiplets, and they look like this. This is a Broadcom Qumran 3D, which you can now buy. That's about the size of the palm of my hand, much bigger. And for those of you who can see the screen carefully, you will see there are actually 6 separate pieces of silicon in here doing the work. There are 2 of them which are made by Broadcom, and there are 4 of them which are not. They are high bandwidth memory. Why are they doing this? Because they don't need to make high bandwidth memory. People know how to make high bandwidth memory. They can just go down to Tesco and buy them. So they do. This is also much more efficient because they can make smaller pieces of silicon. I think we all know that means better yields. They can mix processes. So for example, the internet tells me, so nothing confidential, Broadcom manufacture with a 5 nanometer feature size, the memory probably maybe 14 nanometer, completely different. This is really exciting. This creates an opportunity for us. A key part of this is that these separate chiplets are connected together using incredibly short interconnects. And we will discuss why that's really important. But in summary, it means much lower power to connect them and much faster. And everyone in this room lives for fast. So let's talk about why you want to make them really short. I'm going to get really nerdy, so I hope everybody likes that sort of thing. Copper tracks. I think we've all seen them on PCBs. Imagine them between a transmitter, such as your router chip, your router multi-chip module it now is, going to your transponder. That's about 10 inches. Sorry, I work with Americans, I apologize. About 10 inches across your PCB. In this room, we love a 1 and a 0, and I'm sure I'm not the only person who has got a birthday card written in binary from friends. That's what your 1s and 0s look like at the start. They have a lovely, very clear, down at the bottom 0, up at the top 1. Very clear, very nice. Diagram at the top. The timing is extremely clear when they transition from one bit to another. Life is good. Until you get to the other end of the track, when life sucks. It turns into mush. Look at it. If you get a bunch of 1s together, you start to lose your 0. You start to lose the base. It all goes upwards. Look at what's happened to the timing. It's filthy. By the way, I should belatedly thank the Net London people for all the careful questions we had in the dry run of this. So there are lots of very exciting footnotes just for them. This is actually for 100 gig. That's one of them, just because it shows it more easily. But the LPO is more about 400 gig, but it's easier to see. So what do? You have to put a DSP on this. You can't receive that. That's rubbish. So to put it bluntly, you have to push harder, and you have to look really carefully at what you get. You have power to transmit into that line, and you have DSP to work out what you're getting back from it. And in fact, as things get faster, you even pre-shape the signal you send so that it's a bit less rubbish by the time it gets to the other end. So in other words, copper is not your friend. So, what do we do about this? At the moment, the sort of pluggables you have, such as the one I've just lost in my pocket, have built into them a DSP. The router chip has built into it a DSP and a line driver. So you are putting a great deal of work to push that signal in and to try and get it out of the mush at the other end. And in between, you have your 10 or whatever inches of copper. If you've ever wondered why your fast ports are often in the middle on a router, shorter copper links. It's not a coincidence. This is an opportunity, however. Those DSPs are getting quite big. So we can be clever and use them for something else. What we can say is, well, this copper stuff really sucks, but the fiber doesn't impair things too much. So let's take out the DSP from the pluggable. Let's make use of the fact that we've got a big old DSP in that router chip and directly modulate the signal, not just through the copper, but straight forward into the laser. And yes, I do mean that. This pluggable is now analog. For everyone in this room who loves the digital world, I'm just going to repeat that. Your high-speed pluggable is now an analog component. But think of the significance of that. It's a lot simpler. It's a lot cheaper. It's a lot lower latency. It's a lot more reliable. Those are kind of good things. Now, I come from a world of long-haul transmission optics. And for anyone who knows that world, you know this signal quality is going to suck. And it's going to suck a lot. But as engineers, it's not about achieving perfection. It's about achieving good enough. And within a data center, it's good enough, given all those advantages. Let's look at some alternatives. Why not go a bit further? We hate copper, so let's get rid of it. Let's move the fiber all the way over the other side. Let's take advantage of that co-packaging. Let's package even more stuff together and put the modulator in that router chip. And yes, these packages get really big. You've just eliminated a lot of that signal corruption. You have improved considerably the quality of the signal here. You have significantly reduced the power of what you're doing. This is great. However, you have created an entirely new way of building a router, which is a bit of a radical shift. So this is a bit more for the brave in the room. One thing, if you're looking carefully, you'll notice is I said modulator, not laser. The lasers are usually separate because, as was said earlier, lasers are nasty hot things which tend to fail just when you least want them to. Because we've put the modulator in here, we now have a really big chip, and if anything fails, you're stuffed. But the laser's the thing most likely to fail, so what people tend to do is put them externally. That keeps a lot of heat externally, it keeps a lot of failures externally. That's really a very useful shift. The next approach to this problem, and as you can see, people have been having some fun in this space, is to take that concept and instead of completely changing how you produce your router module, learn from it, get rid of as much copper as you can, and just put the modulator really close, but as a separate module. Not going to talk much more about this just because none of the fun people that I've been looking at do that, but it is something that's talked about. You can consider it a transition or intermediate option, but people seem to have actually gone straight to CPO or alternative approaches if they wish to. So that's the basic introduction. What does it look like? I told you it was a radical change. Here is the radical change. This is a CPO switch. Notice there are fibers going directly to the module. And when I said that module was big, you can see I really mean it. That's not the size of the palm of your hand, that's the size of practically both hands. Notice also, it's got a lot of electronics in it now. It's producing a lot of heat. You need to get rid of this heat. We are in practice talking liquid cooled only at this point. So yes, for many people in this room, this is not something you're going to buy tomorrow, but maybe in a year or two. Notice also what's at the bottom, we have many, many fiber connectors, and at the top we have those lasers. For anyone who's counting the lasers, you can share those between channels, so it doesn't have to be the same number of lasers as external ports. So there are now some shipping products using it, not this one, but it has started to come out. You can get this stuff. So that's one way of doing really high density short reach interconnect. I define short reach as in the data center or campus, so a few hundred meters, 2 kilometers sort of thing. This is a completely different way of doing routers. Another way is being looked at to just take the way we do it at the moment and think, can we make it denser? Can we make it faster? That alternative approach is called XPO, extra dense pluggable optics. This is taking a completely different approach. This is just saying, let's take the electronics in a module, let's scrunch it up a bit. How far can we scrunch it up and make it smaller? How far can we make it denser? So you can see here the OSFP, standard OSFP on the left, and a module on the right. This module is 8 by 1.6 terabits. It takes approximately 2.5 times the size of that OSFP. So that is a considerable improvement in density. So let's talk about the details. The idea is you can get this in all the usual formats, DSP, LPO, copper, as in 10 base T sort of thing. Make that 10,000 base T. Or long distance, there is an MSA, there's manufacturers, blah, blah, blah. Because of the sizing, I said it's about 2.5 times the OSFP, but if you have marketing people, somehow that translates into saving 75% of the space. Don't try and look at that maths too carefully. This achieves 12.8 terabits per module with 16 modules, so that's quite a chunky router. Notice I'm talking OU, not RU. This is very much designed around the Open Rack format. How is it done? Well, I've got one step ahead of myself. Very simply, it absolutely requires liquid cooling. For those of you who are really observant, do you see the 2 pipes at the back? This is putting the liquid directly into the module. Half the problem with these blooming things is we have to get the heat out of them, and even with liquid cooling, you have to have an interface between a cold plate and the pluggable, and that interface is only ever so good. This time, we put the liquid directly into the pluggable. So that saves a lot of space, but more to the point, it runs it cooler, makes it more reliable. Next, there is a lot of really boring stuff that goes on in a pluggable that you've probably never thought of, like the bent tin around the edges. Who cares? The microprocessor that reads out the DDI information. As the doctor earlier was commenting, there's many exciting pieces of information from them, but it's a very small microprocessor. The voltage converters, it's all really boring. And then there's the DSPs that does the really clever, exciting stuff that we care about. Let's divide those in 2. All that boring stuff, let's make it common. It's all small. There's no innovation there. Just get on with it. Make it common between all 8 channels. Make it smaller. The fancy stuff, let's just take it off. The fancy stuff, where the innovation is going, where all the proprietary whizzy stuff is going, let's reuse that as it is. So that's the idea behind this. is we squeeze down all the boring stuff, but we reuse the clever DSP unmodified, and therefore it can be manufactured more easily. Sorry, I'm saying we all the time. We're not actually making these modules. So that's the general idea behind that. However, in my description, I said I'd suggest to you when to use what. So here we go. Let's talk about that. If you are trying to set up something less than 2 kilometers, and let's be honest here, if you are outside of the big AI clusters, which is to say those super dense stuff just doesn't apply to you, your choices are traditional pluggables or LPO. The others are fancy future stuff you don't need to think about right now. We're mostly engineers here. Let's look at the numbers. Traditional pluggables can go however far you like. LPO just can't. I actually saw in a presentation someone saying 500 meters, but we can do 2 kilometers, so whatever. Short, we can agree on. Latency. DSPs are fantastic, but they are not that fast. LPO reduces that considerably. Just in all transparency, part of this is also removing FEC. Because an LPO pluggable is just a simpler device, it takes less power. Because it's a simpler device, it lasts longer. Just for entertainment, I did a calculation of that into a massive AI cluster. That's the difference between a failure after 2 hours versus a failure after 3 hours in the cluster. And of course, it's cheaper because it's simpler. So, very simply, if you can use an LPO, if it's within 2 kilometers, there is no reason not to. And I've never seen anyone come up with a reason not to. So if you've never come across them, have a look, because really, it's a no-brainer. One thing, when I first looked into this, I thought, well, what kind of idiot buys an LPO-only switch? That's not going to be very useful. That's not flexible. And the answer is nobody, because it's the same DSP. It's the same line off the router. So you buy a switch that can do both traditional and LPO on the same wires. Doesn't care. You just mix and match as you will. OK, so that is the sensible slide. Now let's talk about the mad people. Density is king. Liquid cooling, yeah, we'll have that. Let's talk about CPO and XPO. This is how you achieve some really impressive numbers that, let's face it, we all want to hear about, even if we can't do it right now ourselves. Here it is. Here's the comparisons. So, on the left, the single pluggable, whether it's traditional or LPO. In the middle, CPO. On the right, XPO. Distances. XPO, you can achieve long distance, but, well, probably the main thing is talking about the 2 kilometers. Density. Be very careful looking at this. I am effectively, in order to give you the latest real data points, comparing 2 different years. The CPO is a product that shipped end of 2025. The XPO is shipping in 2026. So you'll notice it looks like the XPO is twice as fast for the very good reason it is, but that's 1 year apart. I suspect that realistically, these are achieving very similar numbers. Production quality, well, I've just mentioned that. Manufacturing process is something worth talking about. CPO is very new. No one really knows what the yield is going to be on the silicon. For anyone who looks at chip production, it's all about yield. So that's an interesting question. The port failure approach is also interesting. The CPO people believe they have solved the problem of ports failing, or at least reduced it to the point where it's not relevant by taking the lasers off. That has yet to be seen. So some fun to be had. Oh yeah, got excited and got my animation in the wrong order. Oh well. This is a chart also that has many very exciting footnotes for people who want to read it. You'll see I've got references here. In particular, I want to be clear that the comparison of density of bandwidth is normalized to one rack unit, which is to say I have divided the XPO numbers down from one open rack unit by the proportional difference of the area of one open rack unit to one rack unit, and yes, that was a fun afternoon. So there's your raw data. Let's summarize. If you are getting plugs, an LPO plug is in practice just another sort of plug. LRO is another variant where you just have analog on the receive side only, but basically the same idea. It's just another sort of plug. However, there is no reason not to use it. If you can use it, use it. It's that simple. Because it's cheaper and better. A very rare combination. XPO and CPO are coming and are very exciting. However, you can only realistically use them with liquid cooling. There are some people who have made them work with really huge heat sinks, but that's a bit niche. As you can see, that will achieve extreme levels of density. Oh, I didn't give you my proof point, sorry. So, at the moment, we have one router which is 4RU, air-cooled, 2RU, liquid-cooled, 1RU, or rather 1OU, XPO, which I think probably tells you everything you need. And the final point, and I really want to emphasize this, because I've had a lot of people come to me and say, oh, can I plug in a QSFP DD to an OSFP? Will they work together? That's not how it works. There are standards as to what appears on the optical interface. However the signal gets onto the fiber, it complies to that interface. It complies to that standard, I'm sorry. So therefore, it's all the same from the other end of the patch cord. So hypothetically speaking, you could take a box today that supported 400 gigs or 800 gigs, and then tomorrow go and buy yourself a super whizzy liquid-cooled CPO one, plug them together, they work fine. There's nothing changes in terms of the optical standards here. This is just about how it gets on to that fiber. That's it. Any questions, please? And as Dave said, last time we tried this, the questions went on for an hour and a half. Let's keep it shorter today.
I mean, there is a moderation there, which is we can't turn up too early, or we'll all be standing there like lemons whilst they run around putting out all the tubs of beer. So,
okay.
Do we have some questions? Great. Bear in mind, if you guys don't come up with some questions, I'm going to start asking questions.
Well, I'll volunteer one before you start. I was just in the lab looking at some of this liquid-cooled stuff, and it's very striking how much leak detection stuff they have all over it.
So, this is all very shiny, spangly stuff.
It's very shiny and spangly.
Yes. The question I would ask is, for the people in the audience who are just engineers working at ISPs, who are in the, you've got, X many ports at 400 gig in a rack in a telephone exchange somewhere, and they're running national networks. At what point does this start becoming relevant? At what point is this worth, I assume, the extra cost of this level of complexity? Where do people start thinking, oh, I should go and look at that stuff that Robert was talking about?
So I want to very much divide this presentation into two halves. One of which, to Dave's point, is, oh, this isn't working too well, is the mad fairyland stuff. That is the CPO, XPO stuff. It's around, it works, you can play with it, but for most people in this room, that's not today. However, the LPO, you can buy boxes that do it today, you can buy optics that do it today. So to your specific question, if you have a switch with a bunch of 400 gigs, you should be using LPO today. It's that simple. If the box can take it, which not all 400 gig boxes can by any means, you do need to specifically engineer the PCB tracks to do LPO. So as we talked about at some length at Net London, the signal impairment through PCB tracks is horrific. So just because the chip can do LPO does not mean a card with that chip can do LPO unless you have specifically engineered those PCB tracks to be as well optimized as you can, which means putting earth planes above them, earth planes below them, earth planes around them, effectively trying to make almost coaxial cable out of a multi-layer PCB. That is a very specific piece of router design, which is why quite a lot of routers cannot do it. But if you have a router that can, you should use LPO. It's that simple. Cool. Does that answer that question?
I believe so. And I can see some people at the mic. Please go ahead.
There are people at the mic. Hi, Greg Choules, ISC. This might just be a numpty question, but when you say liquid cooled, what liquid are we talking about?
Someone in the room can probably correct me, but I think it's 25% glycol with water, usually. Okay. The percentages can vary, but it is basically water-based, so yes, you really do not want this flowing over everything and short-circuiting stuff. I don't know whether you saw, actually, let's go back. Oh, stupid thing, it's from over here, sorry. If I go back to the picture, go back. I broke it. Stay. Right, hopefully you can see the picture here. Hopefully you can see the red pipe and the blue pipe, where the blue pipe's the cool water in, the red pipe is the hot water going out. If you look carefully on this, you will see there is more water flow. So it's really interesting looking at these devices. Half of the volume of these is often actually taken with water management just to get it everywhere. So for example, if you look at a water-cooled, a liquid-cooled standard router that's got normal pluggables in the front, half the water ends up going to the pluggables because that's where half the heat comes from. Because the key thing is, in a properly liquid-cooled systems, there are hybrids, but in a properly liquid-cooled system, there's no airflow at all. So everything has to be liquid-cooled if it produces anything more than very small amounts of heat.
Cool. I believe there's, two more people. Mike, please go ahead.
Hello, Rob Evans from JISC. So apart from being faster and smaller, is there much of a conceptual difference between LPO and, say, CFP2 ACOs? Is it the same sort of, basically, analog interface between the pluggable and the TSPs on the main board?
That is a very interesting question indeed. So you'll forgive me, ACO is sort of before my time in optics. I am aware it is an analog interface, as you say, and therefore would share a lot of the properties here. However, I'm afraid I just don't know it in detail enough to go beyond that point. But I think I see what you're saying, and I agree with your general principle without being able to specifically answer you, except to say that, as you correctly say, ACO is very much many years ago, and LPO is very much where we are now. One absolutely critical point, of course, is ACO is about coherent optics, and this is not coherent optics. This is just straightforward normal optics.
Okay, cool. Thank you.
A key part of that, by the way, is for anyone who likes long-haul transmission optics, where it's all about getting lots of data into one wavelength, because this is all really short stuff. This is mostly about many parallel 100 gigs. So, for example, you do 800 gigs as 8 separate 100 gigs, either 8 separate wavelengths or 8 separate fibers. This is not about being clever with the transmission side. Dr. Steiner had a feeling you might stand up, mainly because I got rude about your DDI data.
No, it's all good.
Gentlemen,
all
don't
good.
fight. Don't fight.
Thanks for mentioning it. We will fight later. No, I have one question about immersive cooling. What's your opinion about immersive cooling? Have you done this at Arista, or is it something you prefer to avoid?
So the products we have announced are not immersive cooling. They do use piping in much the same way that was pictured, although that's not our product. So that's the short answer. And so everything had heat exchangers on it to the liquid. Where are you going with that thought, please?
Well, maybe you could use already existing transceivers with immersion cooling. That is like a thought I had. I have seen in other companies they are trying out this, but the disadvantage is that the special liquid you have is like some oil-based liquid, and you have to clean up the devices and so on if you want to exchange the liquid. So I see a big disadvantage with it, but yeah, I was interested if you have considered it. Because
yes, I mean, immersive cooling is a very good way of sort of retrofitting equipment that was never designed for normal liquid cooling. Obviously, we are now designing stuff directly for racks that were set up on day one for liquid cooling, and therefore this way, with self-sealing connectors to make sure we don't accidentally do immersive cooling, is as you know, very effective, very clean, very tidy. You don't have to mop up quite so much. But yes, immersive cooling is a very exciting technology, I do agree, just not the one that I'm currently familiar with. What is your view? Is your view that the future is primarily designed around piped liquid cooling, with immersive perhaps being used for retrospectively converting stuff? Or do you think that stuff would be designed for immersive?
I think piped is the future, but I mean, it's hard to tell, obviously. Because of the disadvantage with this liquid, you have to exchange it, it must be clean, and I think it's also scary to think about you are putting liquid into your electronics. I think that is also something that people scares out, because we are used to it, that when you put water into it, it short circuits. And
well, I couldn't agree more. So that's why immersive cooling has always somewhat scared me. For anyone who doesn't know, that's where you literally just waterproof the edges of your circuit board and pour coolant into it with a circulating mechanism. Whereas, as you can see from these diagrams that I can never get back to, you pipe water back to somewhere specific. So I mentioned as a flippant aside, but I'll now talk more seriously about leak detection. With this sort of mechanism, you actively have leak detection everywhere, because although all of the connectors are instantly self-sealing, so you should never get a drop off them even if you yank stuff out and shove stuff in, pipes are going to burst sooner or later. The idea is the rack shuts itself down instantly and depowers itself as soon as it detects a leak, for exactly the reason you mentioned, which is that glycol and water is conductive, so you do not want it going over your electronics.
One short last question. This device, how many leak detectors does it have? How many sensors for leak detection?
So again, this isn't our product, so this is a prototype that Broadcom did, so I can't talk to this one. I can only talk to I can only talk to our products, and there what we actually have is magic string, which is a leak detection. So the magic string just runs all around and all over the place. So if it shorts out anywhere, that detects the leak. So it's not just one specific, it's not individual separate detectors. It's effectively detection running all through the length of that string as it goes all over the device. So I'm afraid I don't know what the specs are, but certainly I can't imagine that liquid could escape over more than about a square inch without being detected. Does that sort of answer the question?
Yeah, it does. Thank you.
I see you and I might be having a beer together later.
Yes. I've actually seen an equivalent thing to that. And effectively on that one, the entire sort of green PCB you can see around the cooled part has got tracks that are interleaved like that. And the moment moisture hits, to link two of them together, it goes, I'm wet. Anyway, I think, yes, there is one more person there. Oh, two more people there. Please crack on.
Hi, Simon Lockhart from Bogons. Steve Jones did a great talk earlier about hollow core fiber. And he talked about one of the challenges being that maybe hollow core fiber needs to go all the way into the optics. Is this stuff being designed around traditional single mode fiber, or is it also taking into account hollow core fiber?
Very simple answer. Everything I've seen is designed around single mode fiber. However, Steve is probably the better person. Where is he?
I saw him run out just before.
Oh, okay, fine. Well, in that case, I can answer without fear of him contradicting me. My understanding, and I could be wrong here, is that it's not, I mean, conceptually you could attach hollow core pigtails to most of these components without conceptually it causing any problems. I mean, I think there's probably quite detailed specific problems.
Logistical problems with hollow core.
So for example, when you bond fibers to a chip, normally you put it in a V-groove that's etched into the chip chemically. And it strikes me that would probably have to be bigger for a hollow core, but I don't really know anything about hollow core, so I'll stop at that point.
Okay, thanks.
So I can give you a very clear answer. This is all currently done for single mode. I'm not sure I see any reason why it couldn't be done for hollow core, but I'm not the expert.
And I think we've got one more.
Greg Chulz again, just briefly. I was doing a little bit of research whilst people were talking about liquid cooling. And in 1985, the Cray 2 did completely immersive fluorocarbon cooling.
Yes, so absolutely. I think the key thing is that fluorocarbons are non-conductive, as I understand it. So that is a massive, massive change from the conductive propylene glycol water-based solutions, which is very, very different. So I think the point you're making is that there is a long and noble history of immersive cooling. Yeah, good, okay, agreement. But I think it's fair to say it has not been widely adopted because it's quite hard to make work reliably and non-messily.
Okay.
Oh, there's someone else at the microphone.
Well, there is one question we've had come in from Slack.
Oh, sure.
Before we get to Steve, just because he's been waiting. Somebody has asked, how big would the liquid cooling kit be for something like that? How much oomph, how much kit do you need to service the liquid cooling of something that size? Which I'm not sure is necessarily something you can answer, but it was asked.
Yes, that's quite a complex question. So I'll give you a partial answer. If you Google a liquid-cooled open rack, you will see many pictures of what looks like a 19-inch rack. It's not, because it's slightly bigger. And if you look, it's got a liquid cooling manifold running down both sides with cold water in, obviously. Cold water in, hot water out. And they are leak-proof connectors, so you can just shove your card in, and it connects to power in the middle and coolant on either side. So that is quite well established, well, by the standards of our industry, technology, which is to say it's been out for a few months. You can then plumb that into your wider liquid cooling system. So this system would be cooled with a closed loop of water, so it's not going into the drain. This is just going round and round and round to a heat exchanger, which you would then either connect to an air cooling system or an air conditioning type system, or you would connect into other forms of water to cool it. If you Google, you will, at that point, I can't give you a very clear answer because what you would usually do is not just have this, but you would have a rack full of servers. So you would then have many, 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 many kilowatts of power to disperse. So the heat exchangers are about yay big for a rack this size. But then on the back of that heat exchanger is a much more serious cooling unit, which you would have to dimension according to how many kilowatts there were to get rid of in the rack. So I'm going to be vague at that point.
And I believe we've got one person left in the queue. Steve.
Yeah, Steve Jones from Huber & Sooner. Answering the earlier question, I'm unaware of any hollow core fibers being deployed or looked at the moment. However, and it'll probably be long after I retired, with 3.2 terabits and beyond speeds come in, then why? So there is probably some research institute somewhere in the world probably looking at this from a hollow core fiber point of view, but certainly not today or in the near future.
So what did you think of my statement that probably most equipment we use today could conceptually, trivially have its pigtails replaced with hollow core in order to make its interconnect work reasonably well, excepting the points that I mentioned about maybe bigger V-grooves and things like that.
Yeah, the manufacturing side of things I'm not going to comment on because that's well beyond my knowledge and pay grade. In terms of the hollow core fiber to single mode fiber connectivity, then come talk to me later, we have a solution.
Okay, well, sure, yes. I mean, so if we've got all this kit with single mode on it, you could just couple it straight into hollow core. Is that what you're saying?
Yeah, with pigtails or patch cords, yes.
Yes. For anyone who's not familiar with how optical kit is usually made, you see these yellow fibers up here. Those are what I'm referring to as pigtails. Those are very short fibers going from the chip down to here. Those are back-to-back connectors. So when you think, if you take an optical amplifier and you think you're plugging things into a socket, you're not. You're plugging it into one side of a back-to-back connector with the pigtails being plugged into the back of that back-to-back connector. Likewise, you can see these fibers running down here to the back of these connectors, and then you shove normal connectors up into them. So what that means is that at the moment, these pigtails would all be single mode, and therefore, for Steve's point, you'd then have to couple from single mode to hollow core either here or somewhere else. Did that line up with what you were saying? Is that compatible? Good, okay, thumbs up, we like that.
And I think on that, I won't say run out of steam, I think we've come to a natural point there. I personally very much enjoyed that. Thank you very much indeed for joining us. A big hand, everyone, for Robert. Thank you very much indeed, sir.